All right, everybody, let's get started. So next we have our next keynote presentation today. This actually comes from Dr. Claire Marvinney here at Oak Ridge. Claire is a staff science in the Quantum Computing and Sensing Group. She's also one of the PIs in the Quantum Science Center. She works very closely with me on the Quantum Computing User Program. So I will turn it over to Claire to talk to us about quantum sensing with squeezed light. Claire.
Wonderful, thank you. Thank you for that introduction, Travis. I'm very happy to be here today to talk about quantum sensing with squeezed light. I am a staff scientist. I'm in my early career still. I've been a staff scientist for 3 years, and I was a postdoc here at Oak Ridge for 3 years prior to that. And I want to start by giving some acknowledgments because the work that you're going to see today isn't just from me. My boss, Alberto Marino, really developed a lot of the optical systems you'll see today, and a previous colleague of mine, Raphael Puzer, did so as well. Matthew Feldman is a postdoc who has worked closely with me on this work, and then colleagues Ben Lowry and Yunyi Pai on some of the work on magneto-optics really put in a lot of work towards that. So this is a very collaborative effort kind of on squeezed light that you'll get to see today when I talk about the experiments that we've worked on. So I really wanted to thank everyone to start. So you've seen quite a range of quantum information science applications through your summer school already. And you know that in the past 3 decades, and we've really taken off in the amount of research in all of these areas. And this includes the area of quantum sensing. You had a very nice presentation last Friday on quantum sensing from colleagues at NIST. And I may have had a keynote that touched on quantum sensing as well. So we're going to focus on quantum optical sensing as I talk today. Why quantum sensing? What is the reason we might need a quantum sensor? 2 of the big reasons, and I know on Friday I pointed out microscopy and microscopes and telescopes, right? Things that are big, things that are small. Properties of new materials, novel quantum materials, where there's some very small change that you want to see and observe. And then the mysteries of the universe, trying to understand what is dark matter, what is dark energy in these very small particles and fields that exist that we don't understand yet. And we're going to probe these with light, so systems that we can probe optically. And in a quantum sensor, when can we go to a quantum sensor? In the case, so if we're looking at noise power in our measurement, and if you're looking at your TV, this would correspond, the shot noise limit corresponds to that white noise. You may not have ever seen a TV look like this, but you might have heard it on the radio. It's that fuzziness, right? And we're trying to see a signal that's below that. And so if that signal is just so small that you actually need to lower your noise limits and even to see it in the first place, it's one of the cases why we might want to use quantum sensing. If you're power limited, that's another reason. So you can't increase your power anymore, or your power is going to damage the sample or add heat, change the state of what you're sensing. If your integration times are prohibitively long and you want to be able to do them faster, say because you want to see something time resolved, or just you don't want it to take a week to take this measurement. So what is optical sensing first? Because we're going to focus on sensing with light today in this presentation. Right, there are physical dimensions of the electromagnetic wave. It's a lot of different properties. The wave has polarization, it's got a spatial structure, amplitude and phase, frequency and wavelength, energy and time. And so we can use changes in these to use the light as a sensor. So what is a sensor? We have some physical field. In the case of an optical sensor, that's going to be an electromagnetic wave. It's going to transduce some information from something, in this case, material or a mirror and an interferometer, something that's changing. We've got some readout method with some, raw signal current from that. You can amplify that. There's some back-end analysis that's going to change this analog signal to something that's digital that we can actually comprehend and analyze. There's noise in all of these components. So technical noise from all of your electronics, and then there's a standard quantum limit of the system and of the probing optical field, right? And so, there's some noise floor, some signal amount, and we have some control over that noise as we kind of get to the limit of the noise in all of our back end, but we also eventually reach that standard quantum limit of our probing optical field. So how can we improve upon this is what I'm going to talk about in part today. There are quite a range of sensors that use optical readout. Of course, your cameras, right? Imaging devices. Chemical sensors use optics. There are long-range sensors like LiDAR, magnetometers, atomic force microscopes, of course, interferometers use lasers. So a lot of different types of sensors that will benefit from quantum noise reduction with squeezed light. What are we actually doing, right? So these sensors first have to be at their state-of-the-art sensitivity. And so kind of any sensor, you've just got a range of, so they're limited detection, the small signal they can see, and the analysis time here are the axes on this plot. And you've got a range of sensors that you're working towards getting towards this dashed line. Once you reach that dashed line, in order to cross over it, we need to improve upon that signal to noise ratio by changing the noise properties of the probing field. And so pushing into this gray region means faster detection times and lower detection limits by actually changing the noise level in the system, which would enable shorter detection times, lower optical powers, and improve sensitivities in our sensor. So in our measurement, we're trying to do some estimate of a parameter. There's some measurement uncertainty of that and some response of our detector. So then we have the uncertainty in our parameter P. And again, in optics, we can use intensity, phase, polarization, frequency of the light. So in the next few slides, I will begin talking about how we can actually generate that quantum-based sensitivity by improving upon the noise source, the noise in our probing field. And coming back to this picture of what a sensor is, so we're improving the signal to noise ratio by reducing this noise floor, right? So what is squeezed light? What is quantum sensing? You've heard about other quantum sensors already. I know you heard a great deal about atomic clocks on Friday and other types of sensors. These are all actually, while there's still many experiments in the laboratory that are, groundbreaking, there are also commercial systems for atomic clocks, electrometers, magnetometers. They're all based on quantum systems. For optics, though, there is one very big experiment that I imagine everyone has heard of, LIGO, right? The big gravitational wave interferometer. And in this, the sensing of that gravitational wave won the Nobel Prize. The initial sensing of a gravitational wave did not require quantum optics. It just had a very big interferometer with a lot of power. Except the current versions of this interferometer are actually injecting squeeze light into the interferometer. So the interferometer, you've got the two interferometer arms here. I'll talk about interferometry a little bit later in the presentation. And the squeezer comes in. This isn't actually a bright field. This is a squeeze vacuum state because they're using very high power field in the signal that's going into the interferometer itself. But they have vacuum ports, so they have beam splitters, and they have a vacuum state entering the interferometer from that beam splitter. And so they're actually reducing the noise that's entering in that vacuum state so that they can see a smaller signal. I'll come back to some of this readout uncertainty, what that means later. But if you take the classical state, so here we've got the noise in the system versus the measurement frequency. Here they're going from 30 to 3000 hertz. And you're seeing some signal. The classical system with no injection of squeeze vacuum is the black line. Once they actually do their squeeze light injection, they initially get green, and then this even newer version that was this PRX paper last year is frequency dependent squeezing, allows them to get below the black curve everywhere. You see that there's actually frequency dependence to the squeezing, and so if they don't change the properties of the squeeze light with frequency, they don't actually get an advantage at low frequencies. So I'll come back to that in a little bit, but note that this experiment, it's actually detecting signal that is not possible to detect without the injection of squeeze light. We've reduced the noise floor below what is classically available. And so this actually has a quantum advantage for a sensor. Quantum noise, what is it? And it's the result of quantization of the field, the photons, and the random distribution of the photons. So as photons randomly arrived on the detector, we get some distribution that depends on the optical power. So this will scale as you increase the power, the width of this uncertainty will increase. In a classical system, the minimum case of this is the coherent state. It's at the shot noise limit. So a laser, a coherent laser, is a system that is at the shot noise limit. In the electromagnetic wave, we can look at the amplitude and the phase. These two quadratures are what I'm going to talk about as we carry on talking about squeeze light. The amplitude and phase are conjugate variables of the light wave, and they must satisfy the uncertainty principle. Heisenberg's uncertainty principle, the uncertainty in the amplitude and the certainty in the phase must be greater than or equal to 1. In the coherent state, if we look in this diagram here, you have phase, the uncertainty in phase, phase on one axis, amplitude on the other. And we look at, this is the displacement, it's the amount of power you apply. The uncertainty in this position is equal in the amplitude and the phase. So that's a coherent state of light. And it is, this special case of where this equals 1 in the uncertainty principle. It's the shot noise limit. Well, what does squeezing do? Squeezing actually still meets the Heisenberg uncertainty principle, but now we're changing the uncertainty and the amplitude at the expense of the uncertainty in the phase, or vice versa. So if you look in that same space, this the circle now becomes an ellipse, and we've squeezed one axis at the expense of the other axis getting bigger. What does this look like in the wave? Well, a coherent state is just an equal fuzzy line, sine wave here, right? And the uncertainty in the amplitude is equal to the uncertainty in the phase. But in a phase squeeze state, we actually begin to understand where it crosses that zero crossing better, but we now know less about that amplitude. And vice versa. In the amplitude squeeze state, we now have an improved understanding of the amplitude, right? The uncertainty there is less, but we now know less about the where it crosses the 0 point. How do we generate the squeeze state? Well, we need a squeezer, some nonlinear process, and it's going to emit a pair of photons into the field. And when we do joint measurements, we can actually see the amplitude squeezing case here. So the uncertainty in the amplitude is related to the squeezing value in this nonlinear process. The squeezing value is related to the nonlinearity. So the bigger the nonlinearity, the stronger the squeezing, and the narrower you can get that uncertainty, but at the expense, equivalently, of the anti-squeeze case of the conjugate variable. What does this look like if we're looking at the temporal distribution of photons, which you can directly relates to the amplitude or the intensity of the light hitting the detectors. In a coherent state, there's some randomness to those photons' arrival time. But in the amplitude squeeze state, we actually are ordering them more temporally. And so that the uncertainty in their arrival time on the detector is reduced. So if we're taking that measurement and we've got two fields, and we take a difference measurement between them, we'll actually see, so the classical light here is this green line. And so if there was no squeezing, we've got these two fields, we wouldn't change, we would be at the shot noise limit. But the noise power, as we subtract between the two fields, is actually reduced when you are measuring, when you have an amplitude squeeze state and you're measuring this intensity here. And that corresponds, this amount of noise reduction corresponds to the amount of squeezing. So here we have 5 decibels from -75 to -80 of noise reduction. That is 5 decibels of squeezing. This relates to the squeezing parameter. The maximum squeezing that has ever been achieved is 15 decibels of quantum noise reduction below the shot noise limit. And that corresponds to a squeezing parameter of about 2. So there's this, very limited range right now of what we've been able to access with squeezing, but that is actually quite a large amount of squeezing in a very correlated state. Oops. I guess I didn't quite get my everything into the animation. All right. So what kind of quantum enhancement do we see when we have some amount of squeezing? So you've got your estimated parameter P and the uncertainty in it. You've got from the measurement uncertainty and the detector response. Well, we can look at the squeeze case versus the classical case, and we relate them. So here's the classical sensitivity over the quantum sensitivity. And the enhancement factor is going to depend on how strong a squeezing case we have. But we have to compare the two comparable systems, right? The squeeze case and the classical case to each other to actually see how much we're enhancing the system. So for example, the enhancement factor and the amount of squeezing, actually, you can start with 10 decibels of squeezing. And if you have no losses in your system, if you're at a transmission of 1, your enhancement factor is a little over 3 here. But this quantum enhancement is very sensitive to loss. So if we start having losses in our train before we actually can measure that squeezing value, or measure the system and find where our signal is. If we've had loss, we're going to reduce our enhancement over that of a classical system. So this is one of the main technical challenges of working with squeeze light, and why you don't want to start working with squeeze light until you've reached that shot noise limit, because there are other methods like adding power that are going to be easier because they're not as sensitive to loss as injecting squeeze light into the system will be. Another thing you can do, so we've got the enhancement factor, but you can also see smaller signals. So if you have a classical field with some power, probing some unknown parameter with some interaction, we then have our measurement M and the variance in our measurement M. And this scales with the number of photons that we put into the system. So there's minimum resolvable signal of this measurement. So we've got our signal to noise ratio. The minimum resolvable signal of our measurement initially depends on 1 over n, or your signal to noise ratio depends on 1 over the square root of n. Okay. And if you put in that more ordered physical field, the quantum light, and interact that with your measurement instead, now we actually get an improved scaling with power. So not only are we reducing the noise in our measurement, but we can see smaller signals and that those signals scale better with power. And this is now the minimum resolvable signal scales with 1/n squared, and that signal noise ratio scales with 1/n instead of 1 over the square root of n. So it's better scaling as you inject more power. The type of squeeze source that we work with at Oak Ridge National Laboratory is a continuous variable squeeze light source. And this is what it looks like. I mean, that's an entire optics table. So that's an 8x4. And it starts with, we need some very low noise source laser. And yeah, all the rest of these optics are things that are helping stabilize our light source and also generating the pump and probe I'll show later that need to go into the nonlinear process to create our squeezed fields. And then also on this table is the measurement that we want to do, the sensor that we want to send that into. So we're making the squeeze source, we're stabilizing the squeeze source, and we're sending it into our sensor all in this one optics table. But it's still a lab scale experiment. So we're using a non-degenerate four-way mixing process in an atomic vapor cell. In this case, it's rubidium-85, the isotope rubidium-85. And there are other atomic systems that you can also get squeezing from. However, my colleagues, Alberto Marino down here with his PhD advisor, Paul Lett, they were able to show just how efficient this particular atomic system is for generating squeezing. And so what we do, so we've got this lambda system, and we're going to heat up this cell so we have a higher probability of this absorption to occur in the pump photon. So then we also seed this probe photon, and this is a more accessible state. So there's also rubidium-87, which is part of, it's a larger amount of the natural abundance of rubidium is rubidium-87. But the hyperfine splitting in the ground state is 6 gigahertz in rubidium-87. So it's more accessible in rubidium-85. A lower frequency is just easier to achieve with the electronics that we're going to use and the other optics that we're going to use to access this system. And so we have to do momentum conservation. So we send in the probe at some small angle so that we can have momentum conservation between the emitted pair of photons into the probe and conjugate fields. And so those two fields, it's the joint measurement of them that is the squeeze source. Because they're emission from an atomic system that's heated up, they're actually in a thermal state by themselves. So if you only measure the probe or you only measure the conjugate, you're going to get more noise. But it's a joint measurement between the two that allows us to see less noise. So this D1 line, if we actually scan across the detuning of the probe from the pump, so we set the pump to some frequency, and then we're going to scan how far detuned we have this probe from it to find the position with the most gain, because gain is going to be proportional to our squeezing. And so if you scan the probe, we'll get into the absorption bands of the rubidium. That's where this goes to 0. And then we're looking to sit where we kind of have maximal gain, which ends up being, so if this is where the pump field is, it's 3 gigahertz detuned from the pump field, which is equal to this hyperfine splitting of the ground state of the rubidium. So that's where we have kind of our maximal squeezing. Yes? Continuous. You can make squeeze sources with pulse lasers as well, but we're able to do this with continuous lasers. So. You can use nonlinear crystals to make squeeze sources as well. And often in that case, you need some sort of cavity to get to enough gain to actually have enough squeezing in your system. But here, so, a lot of people use PPLN nonlinear crystals. And you can then generate squeezing at other frequencies. Then we're very limited to the frequency that is at the rubidium D1 line. No, we don't. It's just, there's enough nonlinearity in this atomic process that we don't even need a cavity around our cell. We get enough gain just through heating the cell and getting to this kind of larger absorption state. Again, if you if you heat the cell too much and you have too much absorption, we start having too much loss. And so we lose our squeezing before the photons even leave the cell. So, because we lose the correlations. Both. Yeah, you can actually, depending on the type of measurement that you do. So if you're doing an intensity difference measurement, you're really just looking at the amplitude squeezing of the system. But if you do a measurement, and I'll show this, if you do a measurement with a local oscillator, you can actually tune between amplitude and phase squeezing by selecting the phase of the light. So what does this actually look like? I just wanted to show like the optics. This is just the optics for generating the squeeze light up to, this is a little oven around the rubidium vapor. So that is our nonlinear mediums in here. It's after this point. So all these optics are generating the squeeze light source with our pump fields. We generate a probe from the same laser. So the noise properties are similar. And we inject both into our cell, and we'd actually, then we reject most of the pump because that is not squeezed. And so we don't want photons from that interacting with any of the rest of our measurements. And we generate the probe and the conjugate, and they're at some angle. So the farther away we get, the more divided they are. So what does this look like? I showed a previous figure, but with rubidium 85, the maximum amount of squeezing that has been achieved is about 9 dB. And this is after the cell. And there's a little bit of loss in the cell as well. So the actual squeezing value before it leaves the cell is a bit higher than 9 dB. So this is a very correlated system, really squeezed and anti-squeezed the intensity and phase. And so this is the shot noise limit. You can see that this is also a frequency dependent measurement. At low frequencies, we end up being limited by just environmental noise sources and also the noise in the laser as well. So if you can reduce the noise in your laser using cleanup cavities, you can actually push the frequency on the lower side down. Yes. Yeah. Sorry. Oh, that's heating. So we want to heat the cell. So we're actually just, putting current across the cell so that it's creating an oven. That's how we heat up the system. There is thermal noise. So individually, if you just measure the probe or you just measure the conjugate beam by themselves, they have added noise. They're above the shot noise limit. But the joint measurement of the two of them, because of the correlations and their amplitude and phases, we actually get noise reduction in the measurement. And that's what I'm showing here, is that this is the joint measurement. The difference measurement between the probe and the conjugate actually can get us up to 9 dB, even with the fact that individually those states are thermal states.
So with the beams, there seems to be a beam in the middle.
Yeah, so that is the residual pump beam. So you can actually see that, they are overlapped in the cell, and by the time we get a few inches away from the cell, there's some space between them. We use cross polarization. So we're not another type of continuous variable squeeze light source you can make is a polarization squeeze light source. We're doing squeezing between the amplitude and the phase, so we can actually use polarization. This is a polarization independent process. So the pump field and the probe field do not have to be the same polarization, and there isn't a dependence on the polarization of the light. So we can use that as a means to reject the pump. But the pump is 500 milliwatts and the probe is, 10 microwatts going in. So there's a huge power difference between the two because we need to have this very large nonlinearity. So we have this large, which is power dependent. So we want the pump field to be high. But we have to reject those photons because we don't want them scattering into our measurement. They're not correlated with the pump or the probe. Sorry, the probe or the conjugate. So they're unwanted. And so the first thing we're doing is we're using a beam splitter, a polarizing beam splitter to reject the cross-polarized pump. And that's just the residual. And we get rid of the rest of that just by using irises and dividing our beam paths after that point. So I was talking about on the lower end, this is limited by your environmental noise sources in your room. Yeah, we have a question in the back. Two questions, yeah. That's correct. So if we had photodiodes that allowed us to get to that larger frequency, we'd actually be able to see the limit based on the nonlinear process in our atomic system. That's limited. Our squeezing bandwidth can be up to 15 to 20 megahertz. In this actual measurement, we're limited by our detecting photodiodes. So they aren't better than 3 megahertz here. That's kind of the bandwidth of the detectors that we're using. Right, the nonlinear process would enable us to get to 15 to 20 if we could measure it. With the photodiodes we use for this, we couldn't get there. So there are various ways you can continue to improve and modify your squeeze light system to optimize it for whatever your measurement region is for your experiment. LIGO, for example, has really worked on cleaning up their lasers. So they push this frequency far down on the lower side. So intensity difference, what does it look like? That intensity difference measurement, we've got our probe and our conjugate, and there are correlations in their arrival times. And so that uncertainty in the intensity of the measurement is reduced. But quadrature squeezing, you can think of it as relative order of the temporal distribution of photons, and we can do 2 different measurements to look at the squeezing of the quadratures. An amplitude difference measurement will show you squeezing of the amplitude, and a phase sum measurement will show you squeezing of the phase. In order to do these particular measurements, we need to put in a local oscillator to our measurement. I want to talk about entanglement a little bit before we get there, because the source that I'm talking about, the 2-mode squeeze light source, has entanglement between the probe and the conjugate beam. So of course, you've seen, the spin up, spin down entanglement, right? If you can't separately describe these 2 cases, if it depends on the measurement of both together, then we have entanglement. So what does that look like for continuous variables? As you add up the sum, we're going to go to an integral of some function of state A and state B. And if we can't factorize it out into a function individually of state A and individually of state B, we have a squeezed source or an entangled source. And so we can take a joint measurement of the quadrature values in order to show this entanglement. So here we come back to the uncertainty principle, and we're going to set this equal to 1. So that's where the 1 over the square root of 2 for the amplitude and the phase measurement come from. So we want to look at an amplitude difference between the probe and the conjugate and a phase sum between the probe and the conjugate. And this will actually show us entanglement if we meet this inseparability criteria, where if the uncertainty in the 2 added together is less than or equal to 2, yes.
So if I have a fiber and then I'm applying this 55%, maybe it's a more of a general question, but like how to inject the noise if there is an outsider attacker, how does he inject the noise into these communication channels?
Oh, so you're talking about like key distribution? Sorry, you're talking about a particular application that's slightly different than a quantum sensor. You're talking about actually sending quantum information over these channels and having some intermediary interacting with that quantum information. And I know there's discrete variable quantum key distribution. And so you need to actually know something, you know, at your nodes in the same way you would do with discrete variable quantum key distribution. You know, you have the information sharing between your different nodes in continuous variable quantum key distribution as well. But I haven't particularly studied that, so I'd have to look in exactly what is that attacker doing in that case. Yes, squeeze light. The question is, can squeeze light be a qubit? Because you can generate entanglement from squeezing. So if you have a single mode squeeze light source, you have you need that squeezer to generate the squeeze beam, and then you need a beam splitter operation. And from that, you can generate entanglement. Because you have entanglement, you could actually build up a system that does quantum computation, because that is the key resource that you need. And there are people working on these types of optical quantum computers. And by people, I mean, there are companies out there. And in fact, we do some research on that at Oak Ridge National Lab as well, but I'm not presenting any of the work that does computation. In fact, Matthew Feldman, who I showed kind of in my acknowledgement slides, a postdoc who works with me, is working on some of the quantum computation applications of this. Yes.
Polarization and PBS first figure, then he can figure out which one is causing the
You could use polarization optics and phase modulation to convert this squeeze state and amplitude and phase, you know, and into a polarization squeeze state using the appropriate optics. I don't have them shown on any of these slides, but you can convert between the two because there are relationships.
that is like base, then what kind of device do you use to like do the measurement?
Yeah, I'm going to shortly after, I just wanted to talk about entanglement, but I'm going to show what the interferometer looks like that will allow you to do a phase measurement in just a moment here. Yes. No, with a continuous variable state, we do not have to go down to the single photon level. We can use bright states of light, and that's so we can have a displacement alpha in these measurements. This whole system is at room temperature. I mean, and the cell is actually hot, right? And so this is not a superconducting qubit state. It doesn't need to be cold in order to generate the entanglement. Okay, so this inseparability criteria, what does this look like? How do we do this measurement, the joint measurement of amplitude difference and phase sum? The most important thing is we have to add in a local oscillator. So we bring in our squeeze field, we have a beam splitter, and we have a local oscillator that we send in. So some other field, and this field has some chi here. That's the phase of that field. And we're still going to take some measurement here. This has a difference measurement, but we can also take a sum measurement between the two arms of the beam splitter. And this is homodyne detection. Okay, so we have the same frequencies coming in. So we need our local oscillator to match the frequency and the mode profile of our probing field, our squeeze field. And I'll show what that looks like in the two-mode squeeze case in a moment. But I want to talk about what does this look like in terms of amplitude squeezing versus phase squeezing as we scan across the phase of the local oscillator. So we have the kind of in our field, the amplitude uncertainty and the phase uncertainty. And so our normalized signal variance depends on these. And this is chi here, the phase of our local oscillator. And I'm going to just kind of step through what the uncertainty looks like at different points. So chi equals 0, we have some larger uncertainty in amplitude because we're doing a difference measurement here. And then at chi equals 1/4 pi, just we're using units of pi for our phase here, we actually get to our minimum. So if this is our standard quantum limit, we're dipping below the standard quantum limit there. And we can continue to rotate the local oscillator phase, and we'll just bounce through this plot. So you just continuously vary the phase, will continuously bounce along this plot. So you actually want to phase lock the local oscillator to that minimum in order to do a measurement that is, in this case, if you're doing amplitude based measurement, something with like you're looking at transmission and so changes in the amplitude matter, or if you're looking at phase, you're looking at some disturbance of a mirror like LIGO, you want a phase sensitive measurement, you would do a phase sum measurement, and you can bounce through this and find that minimum below the standard quantum limit and lock the local oscillator's phase there to that minimum. What does this look like when we do a joint measurement? We use a hybrid junction so we can take the signal from our conjugate beam with its local oscillator and our probe beam with its local oscillator. We actually have to do 2 homodyne detection systems using the 2-mode squeeze light source because there's 6 gigahertz difference in frequency between the probe and conjugate beam. So we can't actually interfere them together on a beam splitter. So we actually have to have a local oscillator for both of them. But if you scan them simultaneously, and at the same time we do both a sum measurement and a difference measurement, you'll see that as one of them increases in noise, the other is decreasing in noise. So when the amplitude difference measurement is anti-squeezed, the phase sum measurement is squeezed. And so this Dwan inseparability criterion, we can then use, the uncertainty in these 2 arms, is it less than 2? And in this case, in this measurement, where our squeezing value for the phase sum and the amplitude difference is around 4, we are meeting that inseparability criteria, so we have entanglement. So in our rubidium vapor cell, we're actually showing that the probe and the conjugate beam are entangled with each other. And you can use a bright state of light here. The local oscillator needs to be higher power, but by about in order of magnitude, but so that you can use the local oscillator to see where that shot noise limit is. But you can still have photons in your probe and conjugate fields. You can also use a squeeze vacuum state, so both work in this measurement. So I talked about the fact that we needed to have a local oscillator for the probe and a local oscillator for the a local oscillator for the conjugates. We actually, in our rubidium vapor cell, we do 2 4-wave mixing processes because we want everything about the property of the local oscillator to match in the spatial mode profile and the frequency of the probing field and the conjugate field. And so when we do that interference, we want to have the best visibility in that interference. So we want these to really match. So we actually generate 2 probes and 2 conjugates. They both have equal everything, and we put more power in the one that we're going to use as a local oscillator to then do our measurements. So next up, I'm going to talk about what some of those measurements are, but I wanted to point out again, just over these past few decades, we've been increasing the amount of squeezing that you can generate in a single system. When I talked about 15 dB, that's not in a sensor, right? When I talked about these being very sensitive to loss. In a practical sensor, the most squeezing typically is around 4 to 6 dB. Once you actually take into account probing some system and seeing some signal below the quantum noise limit, you have losses in that system, and that reduces the amount of squeezing we have in an actual measurement. This includes some of the various versions of LIGO, though I didn't update this plot with the newest measurements from LIGO. But the newest measurements from LIGO I want to come back to. talked about these, right? The uncertainty and amplitude and phase. They can actually vary the which part of the amplitude or phase is squeezed before they inject it into their interferometer. So they actually tune between an amplitude squeeze state and a phase squeeze state by changing the phase of their probing squeezer. And they use this filter cavity for that, and they modulate the length to modulate the phase that then gets injected into their interferometer. And so that they are then varying the phase of this injected squeezer from that of the actual laser field that's in the interferometer to do the measurement. And this enables them to do this part. If they didn't vary, if they did frequency independent, they're just phase squeezed in that case in the interferometer. But at low frequencies, you actually are looking at back action. So the intensity difference, because when you're phase squeezed, you have anti-squeezing in the intensity. It actually adds noise at these low frequencies. And so when they get to a low frequency in the measurement, they tune the squeezing angle so that they're an amplitude squeeze state instead. So they reduce the uncertainty in the amplitude, and thus they can actually get a lower value or equivalent value of the signal in the sensor when they're at low frequencies as well as high frequencies. So this is making it an improved sensor in the broadband and not just narrowband. So what are some experiments that we've done at Oak Ridge National Laboratory using squeeze light? That's what I want to talk about next. First, I'm going to talk about quantum enhanced material sensing experiments. These are some that I've worked on. Oh, and in general, I'm going to focus on a couple, but we've done a lot of different things historically, not me, because I've actually only been working in this field for the past 3 to 4 years. But historically at Oak Ridge National Laboratory, we've done sensors that enable us to see microcantilever displacement, extraordinary optical transmission, transduction of quantum information using extraordinary optical transmission in plasmonic systems, improvements in magnetometry measurements. So all of these we've been able to do using the 2-mode squeeze light source below the standard quantum limit. So in a magneto-optical measurement, I'm going to talk about kind of variations in the probing light field. We're going to use we're going to use circularly polarized light, and we're going to look at differences in the transmitted light that is left circularly polarized or right circularly polarized. And this will be able to tell us something about the phase of the material. So we have some interesting magnetic material. We want to see these smaller signals indicating some phase change or some magnetic domains in that material more precisely than have been previously done. Because these are optically probed measurements, they are at the shot noise limit. They're done with lasers. And so when we actually have some of these materials that really need to be cold, in order, we expect these interesting transitions to occur at these cryogenic temperatures, and we don't want to be perturbing that system by adding too much heat and adding too much power. And so they will benefit from injecting squeezed light. So this is so MCD is transmission through this material. MOC, magneto-optical Kerr effect, is reflection off of this material. Both of these cases, we're looking at some difference in the polarization of the light off of the material that indicates something about a change in the state magnetic properties of the material. And so we've done a proof of principle measurement at room temperature. We're not cold here. And we're doing an intensity difference measurement with our 2-mode squeeze light source. And we calibrate it to the classical probe coming through the same system. So here we're generating our squeeze light source. We send it through a piezoelectric modulator, which is going to that's going to be our carrier frequency. We're switching between right and left circularly polarized light really fast at 50 kilohertz. And so we need to have squeezing at 50 kilohertz in order to see any advantages in our system at our carrier frequency. And then this, our materials, so we put our sample inside our magnet, and then we want to look at changes. It's not just being able to see that we have magnetic circular dichroism. We want to be able to see changes when we apply some magnetic field. And so there are losses in this system. So because there's added noise between the probe and the conjugate, in the probe individually and the conjugate individually, we use some filter on the conjugate beam to match the losses that we have in the probe beam so that we don't have added noise from the conjugate on it by itself. So we want to match the losses in the two beams. Oops. And then if we look at the system, so the classical system, here's our shot noise limit. We turn on the PEM, we have no sample. We have some added noise in this type of measurement due to just the birefringence in our optics. And so that adds onto our carrier frequency. While we are able to get 5 dB of squeezing without the sample, once we add the sample, that adds additional loss. So we go from 5 dB of squeezing to 3 dB of squeezing. So you can already see that, you know, if there's some reduction in transmission just inherent in the sample, some absorption in the sample or reflection off the sample, you're going to have some loss in your ability to have quantum noise reduction. And then our signal is actually this difference this is a difference in two different fields, and you can see that we can observe the changes with field, but this signal is much higher than the quantum noise limit. And so we need to really reduce the additional noise in our optics train in order to get that signal below the quantum limit. But we showed that it's possible, right? That we can, in the sidebands, we have below the quantum limit noise in our system. And so we have to just work on improving the added noise from the additional optics through additional controls, through additional polarization stability, so that as we go through the sample, we don't have added noise on our carrier frequencies, so that we can actually see a smaller signal below the classical shot noise limit. And what I'm showing here is that as we change the magnetic field, we do see the correct trend between the squeeze source and the classical source. They're both tracking and measuring the changes in the circular dichroism of the sample. So continued work to do related to losses and added noise. It's always a challenge when you're working with squeeze light. What is a case where we would be studying a novel material? Well, this is a dilution refrigerator. Do any of you think this is a quantum computer? This is most images of a quantum computer show you this beautiful tiered cake. That is actually the cryostat, and those are copper-coated gold-coated copper plates that are like thermally isolating each stage of the system, so you can get down to millikelvin temperatures that are required for the stable operation of the qubits in a quantum computer. Also, these temperatures are required to study some of these interesting novel quantum materials. And so we need to be able to probe systems in probe materials in these types of cryostats. So that means we have these very long optical path lengths. So what we studied here is if we have kind of like the known losses and the known, and here's what it looks like in that type of laboratory. Again, you have an optical table, you have spectrometers, you have optics on top of the dilution refrigerator. So there's a lot of places where we have to combat added noise in the system. So we have vibration isolation on top of the dilution refrigerator and so on. So as we probe some sample down in our cryostat in some magnetic field, and we inject in, so this is the same interferometer that you've seen before, another way of representing it. Probe and the conjugate are generated in our squeeze, our nonlinear medium here, and these two beam splitters are just injecting loss. So if there's perfect transmission through those beam splitters, they don't exist. But if there isn't, then we're getting a loss in from the other arm of the beam splitter. And that just allows us to study the effect of loss on the resulting signal to noise ratio that we can get out of this system. But this transduction circuit is the part that goes down into the dilution refrigerator. And if we put in real values of the amount of loss going into the optics of the dill fridge, and can we still see a quantum advantage when studying these materials? And that's what we're looking at here. So we actually, at some different amounts of photons that you send in, do we still, and what is the temperature on the, with that amount of photons coming in, how cold is your dill fridge still, right? Your cooling power will dictate this. And so at a real value of the cooling power that we're able to achieve with photons, kind of around here, 83 millikelvin, and a real value of the transmission in this optical system. If we injected the maximum, so if we initially had 15 dB of squeezing, we would have a limit of detection improvement of over 5 dB. So that's the quantum system over the classical system. The improvement is over 5 dB. And what I'm showing here is that if you tune this, the optimal angle for phase sensitive squeezing in this case, so if you tune the local oscillator and you look at the presence of loss, the blue line is similar to what we're showing here. Even with a large amount of loss, we still have squeezing, we still have an improvement in our measurement. And then so this is in the presence of no loss, even with a smaller value of squeezing, more realistic value, something that we have with our system that we have at ORNL, the 2-mode squeeze light source, we still have an advantage in this measurement system for probing magneto-optical materials at very low temperatures. So from there, so that's, it's not going backwards. So that's kind of the end of what I'm talking about with magneto-optics, but something in all of these measurements, I showed kind of imaging capabilities of like different spatial positions of some sample where we want to look at different regions of the sample. So we want to be able to do imaging. Well, we've started to work towards, and this is my colleague Alberto Marino's work, looking at the spatial properties of the probing fields and looking at squeezing at individual positions in the spatial mode of the light. So what does that look like? Here, they have some chamber. They're going to look at changes in the index of refraction of some plasmonic system, and they're using pressure to generate those changes. So that's this little pressure cell here. But the important thing is they have a quadrant photodiode. So we're looking at 4 positions on the sample. So you put a mask on the conjugate because you always want to match what's happening with the conjugate field to what's happening with the probe field. The plasmonic structure is split into four plasmonic structures. And then we're going to read out the signal in 4 different regions on our joint photodiode measurement. And so as the probing field goes through, there are 4 different quadrants, and actually they were able to show that independent positions in this field are correlated with each other. So if you just look at these 2 quadrants, you're still going to see quantum noise reduction. But if you look at not correlated quadrants, you don't see quantum noise reduction. So you can simultaneously look at all 4 quadrants and get 4 different measurements of 4 different positions on this sample. And you can build up to more spatial modes. So this is just that measurement. Here is the shot noise limit, and they're modulating the refractive index at a frequency of 400 kilohertz and looking at that signal on all 4 sensors at the same time. And they're seeing this improved quantum noise improvement in the signal and the minimum improvement in the noise of the system. So you're able to see a much smaller signal. So then they tune the signal strength. And so using the twin beam is another name for the 2-mode squeeze light source. Using the twin beam with even a lower power than what they put to the coherent state, so you reduce the driving voltage of that oscillation at 400 kilohertz. they were able to show that they have an improved signal to noise ratio at every driving voltage with the twin beam on all 4 sensors simultaneously. So this, as we work on isolating further and further spatial modes within the beams, we can really work on building up imaging with quantum noise reduction using the spatial modes of the beams. So it's something we want to work towards. Now, what is an application that uses the interferometry? What's an experiment that we've done there? And we want to scale this because we already have a probe and a conjugate beam. We already have 2 arms of this interferometer. It's a dual homodyne detection. That's what I'm going to talk about now. So what's an application? Well, we want to do phase sensing of some test mass for applications of detecting dark matter. There's kind of 2 different energy ranges that we're interested in this. This is a Quantum Science Center project. Actually, in the material sensing was also a Quantum Science Center project. And here, if you're looking at heavy dark matter, and you have an array of these sensors, you're actually looking for that particle moving through the array, and it's some perturbation of this test mass, because of some gravitational interaction of that particle with your test mass. This requires really, really low sensitivities, or really high sensitivities, really tiny signals. We're not able to achieve this yet, but if we could build this array of a huge number of sensors, maybe we'd be able to see it. Another area of dark matter that you could use such an array for and might be more accessible is the joint motion of all of these sensors together because of some field of dark matter particles that are really low energy. So very light dark matter. In that case, we're thinking about it as a wave, and we'd get just some joint motion of all the sensors at once. In both cases, we're looking for some oscillation of that test mass, which we can read out in a phase-sensitive way with homodyne detection. Yes? That's one of the challenges of building such a huge array. You do have to individually address them. How can we build up the computational resources to actually take that readout? Right now, in the types of sensors that we're studying towards these sorts of applications, we're looking at small arrays, so it's actually accessible. But that's one of the challenges. How do you scale up to such a large array? How do you do the readout of such a large array? So something has to be addressed. So here we would then put our test mass. In this case, we're using a microelectromechanical device. It's some silicon wafer with springs. And so we've got the weight of the test mass, and you can make that bigger or smaller to kind of tune the mass of the sensor. And so we'll look at this in a kind of reflecting off of that sample in this transducer position is the goal kind of initially. We're going to read out the phase modulation of that. So we're going to use our dual homodyne detection scheme. So both arms of our 2-mode squeeze light source, the probe arm and the conjugate arm, we have to do homodyne detection for, right? So we can actually already probe 2 sensors with our system without adding any more resources. So it's already the smallest network. And this system, we can see that even in the presence of loss, we can get an enhancement over this identical classical strategy. So the signal to noise ratio improvement from the quantum system to the classical system can be over 5 dB, and even in the presence of 20% loss. The actual experiment, yes. Sorry, so the noise in the system is based on, first, if you had a classical light source, you're at the shot noise limit. And so the amount of squeezing So our noise in our system is proportional to this nonlinear gain that we get from the nonlinearity in our cell, our rubidium cell in this case, or nonlinear action. So it's just this nonlinear gain G of 5 is proportional to some squeezing value. This is what the actual experiment looked like. Our initial measurement wasn't using those microelectromechanical devices. We just modulated the phase with an electro-optic modulator. Part of the reason for that is we were still developing the technology of the MEMS devices concurrently with this system. So we wanted to be able to show that this would work as this distributed sensor first before we had the MEMS devices that we would be able to measure. And so here we've built the pair of probe and conjugate beams that are going to be the sensor, and they each have an electro-optic modulator. And then we have, again, the probe and the conjugate local oscillators that we're using in the homodyne detection that we can scan the phase to lock it to the phase squeezed case in the phase sum measurement. In this case, we are able to show that we can preserve the quantum noise reduction in this in this measurement of both arms. And other people have been studying distributed quantum sensing. I'll go back to the previous slide in a moment. Other people have been studying distributed quantum sensing, but nobody had shown kind of inherently with that 2-mode squeeze light source that you could get this benefit from using both arms. So it's kind of surprising that that hadn't been done yet. So we really wanted to just show that using both arms in the interferometer does that we already have. We don't have to do a beam splitter network like you would have to with a single mode squeeze light source. We inherently have a distributed network already. We are able to preserve the quantum noise reduction of almost 2 dB, and we're able to get that classical enhancement that you would expect from the fact that we have we're probing with 2 sensors. So we see the 3 dB of signal to noise ratio improvement by probing both sensors at once. What we're building up to, though, is if you start with a 2-mode squeeze light source and then you add in a beam splitter network, the fact that the 2-mode light source has entanglement means you're not probing with independent quantum states. So we already know that if we're going from classical light to quantum light, that we're going to get this improvement in the minimum detectable signal from 1/n to 1/n squared with the amount of photons injected into the system n. What about the number of modes d here that we're probing with? And so if you're doing independent quantum states, there's no additional advantage as you increase and scale up the number of modes. And somebody asked, how do you deal with the fact that you're probing all these sensors? Well, we can probe less sensors for the same sensitivity if we inject an entangled light source into this system and improve that scaling with the number of modes. So now we'll have the same sensitivity with less modes because we're injecting with entanglement. And so we studied that specifically for the 2-mode light source, squeeze light source, and showed the moment you get beyond 2 modes, you're going to get an enhancement additionally from the entangled case over the separable squeeze case with the number of modes that you have. And in fact, that scales with 1/m squared. And so we want to work towards these types of systems where we're not only taking advantage of squeezing, but we also use entanglement to kind of reduce the amount of resources needed for these types of sensor arrays. So recapping what I've talked about today, so that's the end of the experiments that I'm showing. We can see that you can use light to transduce a signal in the sensor, and that quantum light, squeeze light, can reduce the noise floor in those measurements. You want to be able to use this in certain types of experiments where you're already at the shot noise limit and where it's hard to increase the power in that measurement, or you want to reduce the integration time, or you just have no idea how small that signal is going to be and it's below what you can currently observe. So we're building up towards being able to observe some of these very tiny fields that could exist out there in the universe. And again, I want to thank everyone who worked on these projects. Are there any additional questions? Yes, over here. So the qubits, so you'd need squeezing in the microwave regime. And there are people who are working on that, but it's a challenging problem. You have to actually have squeezing at a different frequency range. These are all optical frequencies that I'm showing here. Yes.
So what's the difficulty to just use this for a quantum computer?
The difficulty of using this for a quantum computer is the scale up. I think that's a challenge with all quantum computers, scaling up to a large enough number of modes for the entanglement. And of course, I showed how sensitive to loss these systems are. So it's not only the scientific challenge of how do we scale up to all of those different modes, but it's the technical challenge of reducing the losses while you scale up.
No, I mean, but can you just have like a whole bunch of lasers?
What you would need is a whole bunch of squeeze states
Right.
entangled with each other.
Yes.
Yes. So you can start with one laser with a really high amount of squeezing and do beam splitter operations. You can start with a bunch of different individual squeeze states and use beam splitter operations. A lot of it is developing those resources and then dividing them.
But still, like, you don't even have to go down to single photon level.
You do not need to go down
Right,
to the
so-
single photon level when you're working with continuous variable quantum optics.
So
You
the-
can work with a bright state of light.
Right, so the fact that you need like a lot of power shouldn't be like a huge problem, right?
Right. I mean, you're not going into dilution or like I pointed out that there are some sensing applications where we might go to cryogenic temperatures, but for computing with quantum optics, you do not need to go to cryogenic temperatures.
So why, sorry again, so why can't you just use this qubits?
You can use continuous
Yeah,
variable
but-
squeeze light as the qubits, the entangled states for quantum computation. But all of the quantum computers, from my understanding, I mean, we're still in the NISQ era, including in quantum optics. And quantum optics just hasn't been as developed as far along as some of the superconducting states for quantum computing applications. It's not because there isn't an interest.
Right.
There is an interest and people are working on it. And we are working on it as part of the Quantum Science Center.
So the difficulty is you can't have half-die gates. Is that
The types of operations you can do have to be something that can apply to the Gaussian state of light. But there are comparable gates in quantum optics as there are to discrete variable systems.
Other questions?
Yes.
Achieve? And are we talking about using frequency combs before squeezing to generate?
You could additionally use the frequency degrees of freedom and frequency combs to generate kind of more states for your entangled light source. That is an option. It's not one we're considering with the rubidium vapor, but with an OPO, you could work on that exact system. And there are other groups. I don't have a slide showing who, but there are other groups and other companies working on that.
So all of that was especially modes entangled, like of entanglement of different spatial modes of light.
That's something
Okay.
we are doing
Yeah.
and aiming to do with the squeeze light source. This is entanglement and building up quantum computation with the spatial modes. Yes.
Yeah, I was wondering how large of D have people been able to demonstrate? So when you're going from into this rather than a squeeze state that has
Oh, the number of
individual
modes?
Yeah, like how big
It's
have
3 to
people been-
4, and it's not with the rubidium vapor cell. It's with a kind of OPO system. They've done 3 to 4 using beam splitter operations.
I see.
Yeah.
What is the fundamental limit on that? Like, I guess, what is the main limit on?
The main limit is, I mean, it's resources, and some of that is the quantum resource itself, the amount of squeezing you start with before you start splitting it.
Okay, let's thank our speaker.